Welcome to Unit 2, Video 4, Gas Laws. By the end of this video, you should understand the qualitative relationship between amount of gas, gas volume, gas pressure, and gas temperature. You should be able to make predictions about the effects of changing one of these variables on another variable. And you should be able to perform calculations using the combined gas law. Let's start with Avogadro's law. Avogadro's law relates number of gas particles to volume and tells us that as the number of gas particles increases, the volume increases. This shouldn't surprise you if you've ever blown up a balloon. Think about what happens as you blow into the balloon. You're adding gas particles and the volume is increasing. Here's a picture illustrating that. Here we see that in the container on the left, we have fewer gas particles than in the container on the right. Therefore, the container on the left occupies a smaller volume than the container on the right. This is a directly proportional relationship, meaning as the number of particles increases, the volume increases. It's important to note that for this relationship to hold, temperature and pressure must be constant. Here we see that both temperature and pressure are constant because our thermometers are measuring the same temperature and our pressure meters are measuring the same pressure. Looking at this graphically, we again can confirm that it's a directly proportional relationship between volume and number of gas particles. An interesting consequence of Avogadro's law is that equal volumes of gas at equal temperatures and pressures will always contain the same number of particles. Take, for instance, 3 different samples of gas, argon, nitrogen, and hydrogen. If they all are at the same pressure and temperature, and they all occupy the same volume, they will all contain the same number of particles. Notice they don't have the same mass, however. This is something you should consider. Why don't they have the same mass? Moving on to Charles' law, Charles' law deals with the relationship between temperature and volume. It tells us that as temperature increases, volume increases. Again, looking at a picture, we see that the container on the left has a smaller volume than the container on the right. The container on the left also has a lower temperature than the container on the right. This again is a directly proportional relationship. As temperature increases, volume increases. Here's a graphical representation of this, which again confirms that we have a directly proportional linear relationship. Also note that here the amount of gas, as represented by the number of particles, must be constant, as should the pressure. Again, our pressure gauges show the same reading. Charles' law is actually the basis for the Kelvin temperature scale. Notice if we graph the volume-temperature relationship of several different gases and extrapolate them all to 0 volume, all of them extrapolate to the same point, to negative 273.2 degrees Celsius. This number should ring a bell to you. Recall that to convert from Celsius to Kelvin, we add 273.2, or 273 if you're rounding. This is the basis for the Kelvin temperature scale. The Kelvin temperature scale places 0 at absolute 0. This is the point where gases occupy 0 volume. Now, of course, this is a theoretical limit, because what would it mean for a gas to occupy 0 volume? But we've actually gotten pretty close. Scientists have been able to achieve temperatures very close to absolute 0. There's an equation for Charles' law that looks like this. Here we have V1 over T1, or initial volume over initial temperature, equaling new volume, or V2, over new temperature, or T2. What's important is that the temperature here must be in Kelvin. As we just saw, Charles' law is the basis for the Kelvin scale. This brings us to Boyle's law. Boyle's law relates volume and pressure and tells us that as volume decreases, pressure increases. Here, the container on the left has a smaller volume and a greater pressure than the container on the right, which has a larger volume and a smaller pressure. This is an inversely proportional relationship, meaning that as volume decreases, pressure increases. Notice the graph here is a little different. It's not linear. We'll talk about that more in class, but do notice that as volume decreases, pressure increases. In this case, amount of gas, as indicated by the number of particles, and temperature are both held constant. Boyle's law looks like this mathematically. Initial pressure times initial volume equals new pressure times new volume. Finally, Gay-Lussac's law relates temperature and pressure and tells us that as temperature increases, pressure increases. Here's a picture showing the container on the left, which has a lower temperature than the container on the right, and it also has a lower pressure than the container on the right. This again is a directly proportional relationship. As temperature increases, pressure increases. Again, a graph showing our directly proportional relationship between temperature and pressure. And in this case, amount of gas and volume must be held constant. Notice both containers contain the same number of particles and occupy the same volume. The relationship here mathematically can be expressed as initial pressure divided by initial temperature equals final pressure divided by final temperature. We can actually take all of these equations and combine them into something called the combined gas law, which looks like this. Initial pressure times initial volume over initial temperature equals final pressure times final volume over final temperature. This is convenient because it actually has all the equations in one. Notice, if we hold pressure constant, we're left with Charles' law, V1 over T1 equals V2 over T2. If we hold volume constant, we're left with Gay-Lussac's law, P1 over T1 equals P2 over T2. And if we hold temperature constant, we're left with Boyle's law, P1 times V1 equals P2 times V2. So you really only have to memorize the combined gas law in order to do any calculations. And again, temperature must be in Kelvin. Let's work through some sample problems together. In this problem, we have a gas at a temperature of 15 degrees Celsius with a volume of 2.58 liters. We're asked what the new volume will be if the gas is cooled to 3.8 degrees Celsius. Notice in this problem, pressure is held constant. Therefore, we can eliminate pressure from our combined gas law and focus only on the volume-temperature relationship. So let's start by determining what our variables are. On the right-hand side, we want to determine V1 and T1. Both of these are given to us in the problem. V1, or the initial volume, is 2.58 liters, and T1, or the initial temperature, is 15.0 degrees Celsius. But recall, we need to convert this to Kelvin by adding 273, giving us a T1 of 288.0 Kelvin. Looking now at the other side of the equation, we need our V2 and our T2. In this case, V2 is what we're trying to find, so that'll be our X. T2 is 3.8, but again we need to add 273 Kelvin, so that gives us a T2 of 276.8 Kelvin. Now we can plug these values into our equation. So we have 2.58 over 288.0 equals V2, or our x, over 276.8. Do the math, and you get a V2, a volume of 2.48 liters. Now, let's check some things. Is this number rounded to the proper number of sig figs? Well, it appears as though our smallest number of sig figs is 3, and our value has 3 sig figs, so we're good. Does it have a unit? Yes, it does. Liters, that's good. Does it make sense? Well, let's think about the volume-temperature relationship. We know that as temperature goes up, volume goes up, and as temperature goes down, volume goes down. In this case, the temperature has decreased, therefore the volume should decrease. And it does. 2.48 is smaller than 2.58, so this is a reasonable answer. Let's try another example together. In this example, we have 1.0 liters of gas at 0.25 atm and 75 degrees Celsius. We then cool the gas to 50 degrees Celsius and the volume decreases to 0.46 liters. We want to know the new pressure of this gas after this change. So let's start by identifying our variables. On the left-hand side, we have P1, we have V1, and we have T1. Our P1 is 0.25 atm. Our V1 is 1.0 liters. And our T1 is 75 plus 273, which gives us a T1 of 348 Kelvin. On the right-hand side, again, we want P2 this time, V2, and T2. Here, our new pressure after the change is what we're looking for, so that will be our X. Our new volume will be 0.46 liters, and our new temperature will be 50 plus 273, which gives us a T2 equal to 323 Kelvin. Now, let's plug these variables into the equation. We have 0.25 times 1.0 over 348 equals P2, which is our X, times 0.46 liters over 323. Solve for P2 and you should get 0.50 atm. Here are some problems to try on your own. Be sure to isolate your variables first by either circling them or underlining them. Also, make sure to check for proper sig figs and units on your final answer. Pause the video here and try some or all of these. When you come back, I'll reveal the solutions. Welcome back. Here are the solutions to the previous slide's problems. That brings us to the end of the gas law video. Let's review our goals. First, we looked at the qualitative relationship between amount of gas, volume, pressure, and temperature, determining which relationships were directly proportional and which ones were inversely proportional. Then we made predictions about the effects of changing one of these variables on another variable. For instance, if we increase the volume of a gas sample and keep the amount of gas and temperature constant, we can predict that the pressure will increase. And finally, we performed calculations using the combined gas law.